Hi everyone, welcome to this new video series on exploring generative AI from concepts to practical example. As you know, in the recent years, the generative AI has shown remarkable progress and utility. And the definition of a generative AI is it should be able to produce new data instances from the known training samples. So this video series on data generation or text generation or image synthesis will be consisting of GANs and autoencoders and variational autoencoders. But in this particular video, I'm not going to talk about either of this. Instead, I'll talk about a very vanilla, simple, naive Bayes algorithm, and we will see how naive Bayes algorithm can also be used as a generative option, although in a limited sense. So essentially, the generative AI applications, when we hear about the term generative AI application, the popular application that comes to our mind would be image synthesis, something like creating new image out of existing images, uh, and combining images, combining the background, or doing style transfer from one image to another image. Similarly, on the text generation side also, there are lots of generative applications. The most important application here is data augmentation. This is what I'll be focusing on in this particular video. We'll see how naive Bayes can play a, a significant role in a limited sense, quote unquote. In some cases, you can use naive Bayes algorithm as well to generate new data. So some of the key algorithms that we keep hearing about is variational autoencoders, autoencoder, conditional variational autoencoder, the many autoregressive models, the 25 odd different variants of adversarial network and transformers and BERT, encoder, decoder, and all of those very high-end and sophisticated algorithms. Now, in comparison to all of these algorithms, what I'm going to be presenting here is a very basic, uh, machine learning, classical machine learning model called Gaussian Naive Bayes. So what we will be covering in this video, when we talk about Gaussian Naive Bayes, the focus is going to be how to understand the idea of generation by using Ganai base, but I'll focus also on concept, how the Gaussian Nye base actually work, what's the underlying statistics, and then we will see how we can, mimic or use the distribution parameters learned by the Nye base model, and then given some data set, how the Gaussian Nye Bayes can generate new samples. So essentially, Gaussian Nye Bayes is designed for continuous data, and we will see how it actually works and how it handles out of core learning. This was one example I presented already in one of the other videos using multinomial Nye Bayes, but Gaussian Nye Bayes can also handle out of code learning. Thirdly, we'll see how Gaussian Nye Bayes can help in data generation, and we will look at a simple data set and do some kind of classification. So Gaussian Nye Bayes is a variant of a Nye Bayes algorithm, especially designed for continuous data. And one of the assumptions Gaussian Nye Bayes makes is the features of the column, they follow a normal distribution and is based on the Bayes theorem. Like other variants of Nye Bayes, this one is also based on the fundamental concept or formula of a Bayes theorem. So the key characteristics of Gaussian Naive Bayes is it is continuous data that is required, and it follows the normal distribution. And another assumption it makes is the features are independent given the classes. That means the two features have nothing to do with each other. So let's take one example data set here, and using this example data set, we will understand the working of the Gaussian Naive Bayes. Let's say you have a column 1 and column 2. This is exam 1 score, exam 2 score, and whether the candidate passed the exam or not. And you notice here the values are numeric in nature. And the outcome variable is a binary variable. Naive Bayes can be used for multi-class as well, but we will stick to binary case here. So where do we use Gaussian Naive Bayes? In most cases, wherever you have continuous features and using those continuous features, you want to classify these samples are spam or not spam. Medical diagnosis, again, continuous features like blood pressure, cholesterol levels, and few other parameters. And you would like to predict uh, presence or absence of a medical condition. Stock market prediction, likewise, again, we have to use continuous data. Image classification as well. If we have pixels and the values, those are numeric in nature. And in those cases, we can use Naive Bayes or Gaussian Naive Bayes variant. So let's look at the sample data set here, like I presented to you earlier, the column 1, column 2, and the last column is simply the binary column. So what we're going to do here is first using the data, we will train the Gaussian Naive Bayes. That means the Gaussian Naive Bayes is going to estimate the parameters for each of the class. So like you have two classes, passed or not passed. For each of the class is going to estimate from the data the necessary parameters. Those parameters are simply mean and standard deviation of each of the column within each of the classes. This is the underlying metric that is used by Gaussian Naive Bayes in its working. So the parameters here, let's say the feature 1, feature 2, and this is the class A. We're gonna estimate the mu and the standard deviation of feature 1 class A, similarly for feature 2 class A, and similarly feature 3 and class A estimate the mean and standard deviation. And for the other class, let's say B, repeat the same process of estimation here. And essentially, what do we do with those estimate is to kind of compute the distribution of feature 1 using the mean and the spread or standard deviation. And you see here the plus and minus 1 standard deviation and plus and minus 2 standard deviation, and so on and so forth. So this is feature 1. Similarly, we will learn the distribution for feature 2 as well. As an example is from iris data, for each of the column, you have the distribution fairly very different from each other. And that's why iris data is very good in terms of accuracies and the model performance, because the characteristics or the distribution of data is quite uh, discriminative. Now, how are we going to use this in our case here? The feature parameters for the example data that we are talking about, the class passed and the feature is exam1 score. In the past class, we will estimate the mean, and let's say the mean is this, and standard deviation is this. Similarly, for the other column, exam2 score, and in the same class, estimate the mean and standard deviation. And for the failed class, repeat the same process here, exam1, exam2, and estimate the mean and standard deviation. Just note down these values. So the algorithm is going to keep those values inside the model and use it at the time of prediction or at the time of out of core learning or at the time of data generation. I'm going to show you all these three cases here. So let's say now we have a new student with the exam score of 70 and 60, and we would like to find out if with this score the student is likely to pass or fail using the estimates the Gaussian Naive Bayes has learned from the training data. So what we're going to do, we are going to compute the likelihood for the new features. New features means the features of the test point. So in order to calculate the likelihood, we will refer back to the distribution that the model has learned. So distribution of exam score, exam one score of the new student or a test student. Let's say 70, exam 2 is 60. We need to find out in this distribution where 70 falls. So roughly I'm putting the value here. Let's say this point represents the score of 70. And likewise on the other column, distribution of the other column, and we would find out where that point actually falls. Let's say 60 falls here. And these points in the language of statistics is also called probability density function. That means given the distribution learned for feature 1, what is the probability that the new student would get 70 as per the distribution learned. Similarly, the distribution learned for feature 2, what is the likelihood that the student would get 60? These values are called probability density function. In other words, is also called likelihood. So likelihood or probability here, exam 1 score 70 pass is this one, or exam 2, which is a score of 60, again the same class, is this much. Now we need to compute the total probability of the pass class, which is basically the number of samples of passed divided by the total number of sample, and let's say that's 0.5. So now what we're going to do is to estimate those here using the values that we have computed previously in terms of likelihood, and those likelihood values will help us in computing the posterior probability here. So the probability density function for the column 1 and column 2, just for illustration, I'm showing it here. So let's say this is the distribution for the class of no. No means did not pass, and yes means pass, and this is the distribution here for both the columns here. So what is the intuition of probability density function or a curve in this case? So let's say probability density function for the column exam 1 score or exam 2 score is essentially taking a specific value on this curve, which is basically a probability density curve. And in other words, this is called Gaussian PDF curve. So this dotted line that you see here represents the Gaussian PDF curve for each of the classes, like yes or no. And the curve simply provides the estimate of the distribution of the feature values, which is basically the exam 1 score. And you notice here at the center that is representative of the mean of that feature 1, and this is for feature 2. The other feature will also have a similar peak. So the curve's peak corresponds to the mean of the feature, and the spread of the data or spread of the curve indicates standard deviation. So when we say estimate the parameters of the column, this is what actually it means. We need to compute the mean and the spread of the data for each of the column and for each of the classes. So for the new data, let's say this is my new data, feature 1, feature 2, and that feature 1, feature 2, let's say it is feature 1 82, and this is exam 1 score. So where that 82 falls in terms of the probability, let's say for the class here, here is yes for the class yes, this is where the point falls. Similarly, so that means this is the curve and going up and up. So this is the highest probability point. And so that means that student getting 82 as per the distribution, the probability looks pretty high here. What about the point on the red line? This is falling all the way down here away from the mean, and this is a low probability here. So that means that student getting 82, which is a feature 1, for the class of no has a low probability. And likewise, on this other column as well, we will find out where that point, in this case, the point is going to be 78, where that point falls on these two distributions. And we will, so essentially, these points are probability values. And we obtain the probability values by using a mathematical function. I'm going to show you in the code how do we do so. So moving on then to the next step, how do we get those points here? These points, like I showed you in the previous one, mathematically, how do we get it? Is by using a mathematical equation which is very familiar to all of you, I guess. Let's say the mean, so the exam 1 score is 82, and the distribution for that column is, let's say the mean is something and standard deviation is, again something. Use those two values, the mean and standard deviation, for this point, which is 82, and that is what is going to return you the probability that we are talking about here. Okay, so these probabilities, just a second, please. So essentially the numerator that is there, that involves multiplying the likelihood or the prior probabilities for each of the class and the features. And that's how we are going to compute the posterior probability for the two classes here. And whichever class has the highest probability will be the prediction for the test point. I'm going to show you the demo of Gaussian Naive Bayes, how it actually works. Um, and then after that, we will talk about how Gaussian Naive Bayes helps us in terms of out of code learning. And then one more use case would be the data generation. So let's take a look at a simple example of how actually it works. I'm going to use a little bit of SciPy to compute the probability density function and some dummy data here. The values, this is the first column is, let's say, exam 1 score, second one exam 2 score, and the classes like yes or no. Separate the data x and y and split the data by class. Why so? Because we have to estimate the parameters like mean and standard deviation for yes call data and no data. So this is where we're going to compute the mean and standard deviation for each of the classes, store those values in variable, and this function is going to return the the PDF or the probability density function of any point given the mean and standard deviation. So in our question, we have two pairs of mean, one for each class. So essentially, for each of the point that you have, let's take that exam 1 score and exam 2 score, and we will plot those points in terms of histogram. And then for those points, we are also going to get the density function so we can plot the curve. And that curve is from the SciPy function called probability density function. Pass the value and the mean and standard deviation, and you will be able to get the plot here. This is the data for exam 1 score and exam 2 score. So this is the histogram here, and this is the distribution for the class of no, and this is the distribution of feature 1 or exam 1 score for the class of yes. And likewise, we are going to compute and understand the distribution for the other column as well. So this is how the Gaussian Naive Bayes is going to compute all these estimates and keep it in the model and use them at the time of prediction. So let's say you have a new point 8278, and then we're going to compute the likelihood of these points 82 and 78, which is simply multiplication here, and then the class probabilities, which is nothing but proportion of number of samples of yes and no. That's the prior probability of the classes. Finally, multiply both of these, and that will return you the posterior or prediction probability of the test point for the class yes and for class no. Whichever is more is the prediction. So in this case, the prediction is going to be yes. So you could mark the points here. Let's say these points that I showed you in my slide is the same plot that I'm using here. So these points are the probability density function of the test points, and based on the density function, you can compute. In fact, you can look at it intuitively as well. My final prediction is yes. And why so? Because of the probability of yes. Notice here for that value for the class yes, and the plot is in the black color and the probability is high. Similarly, here also the probability is quite high here. So that's why you also saw the result in that favor that the test point belongs to the class of yes. I hope you found this explanation useful how Gaussian Naive Bayes actually works behind the scene. And with this knowledge, we will be in a better position to understand how out of code learning works and also data generation. How is data generation possible with Gaussian Naive Bayes? Okay, so that was the example on the working of Gaussian Naive Bayes with the help of a dummy data, and we just looked at it internally. What Gaussian Naive Bayes computes, the mean and standard deviation of each of the classes, and now we also saw prediction, how prediction is actually done finally. Let's go to another use case of Gaussian Naive Bayes, how it facilitates the out of code learning, meaning the incremental learning without dismantling the machine learning model, feed incremental data and compute on or update those model parameters, meaning mean and standard deviation. So the mean and standard deviation are the key parameters that we use in Gaussian distribution, Gaussian Naive Bayes for each of the class. In out of code learning that we are talking about, where the data will be fed to the Gaussian Naive Bayes in terms of batches, we need to recompute the mean and standard deviation incrementally. That means as the new batch comes to the model, these parameters like mean and standard deviation have to be adjusted or recomputed. Essentially, that means the model is up to date with new data. So essentially, I'm just doing a recap. So when you train a Gaussian Naive Bayes with, let's say, partial data, you're going to learn the model parameter in terms of mean and standard deviation for each of the feature and for each of the class. And this will be done using the first batch of data, let's say 100 samples. Then after that, we need to do an incremental update. Essentially, the formula for update is quite easy. The new mean is going to be the old mean plus the new data points for feature one divided by the total number of data points, and that's going to give you the recomputed parameter called mean. And the same way we can compute the standard deviation as well with the new batch. So essentially mu old, mu new, and standard deviation new, and the new data points and total number of data points. These are the values that we need to incrementally update the model parameters. So now comes prediction, which is now going to be the same. Since you have recomputed the model parameter, the process of prediction is not going to change at all. In fact, the new test point, let's say this is the test point, calculate the likelihood for the new data that you have, 82 and 78, compute the PDF. Prior probabilities will change now because of the sample number of samples have changed. So just use the class probabilities or recomputed class probabilities. And then finally, compute the posterior probability for that new point for each of the class using the Bayes theorem. Put those values and you get those probabilities for both the classes. Whichever class is the highest is the prediction. I hope the concept is clear. Let's take a look at the code. I'm going to show you. I'll implement the Gaussian Naive Bayes using Python. Okay, so let's take a look at the out of core learning. How is that possible using Gaussian Naive Bayes? So here I'm going to be using a data set, breast cancer data set. It's a very small data set, but we can simulate the out of core learning. So we're going to divide the data into training and testing. And after that, first initialize the Gaussian Naive Bayes. Now this smoothing parameter is useful because sometimes you don't have a the word in the training set, but the probability turns to be zero in that case. So you need to avoid that. So we just initialize with some very low number called smoothing parameter. Let's say we have 5 batches. That means each batch, not 5 batches, but each batch has 5 samples, and total number of sample, whatever, I think is about 600 samples or so. So 600 divided by 5, so 100 to 20 batches. I'm going to run for each of the batch and we'll do a partial fit. Means partial fit will tell Gaussian Naive Bayes use the new batch data to incrementally update the model parameters like mean and standard deviation. And then within the loop itself, I'll do a testing using the test set that I created up here. So if you notice in the beginning, the results 63% and all that, not very good, but slowly it has improved to 94%. Now this data is very, very small. It doesn't give you a good feeling or a nice understanding of a very low value to start with in terms of accuracy, and then building up with the new sets of or new batches of data, and you get a better result. But I hope you get the idea that how partial fit helps the model keep track of the previous model parameters and recompute the model parameters based on the new batch. I hope this example is clear and was useful. So with that, I think we can move to another use case. This time, our key use case is data generation using Naive Bayes. So let's straight go to the example here itself, how we can generate the new data points or generate synthetic data using Gaussian Naive Bayes here. So let's first take synthetic data, which has a mean of, some random 3 and 5, and a covariance. I'm using covariance to generate the data points for class A. Similarly, I'll have a different covariance, means the spread of data, and that will be for class of B. So those two classes of data, and they look different because this is class A and class B. What we are going to do here is we'll ask the Gaussian Naive Bayes to estimate the model parameters for both the data sets. So this is, let's say now, um, so this is the Gaussian Naive Bayes, and we fit the data that we have created up here. So when you fit, the Gaussian Naive Bayes is going to learn the model parameters called mean and standard deviation. Those mean and standard deviation are kept inside the model using this parameter called theta and variance for standard deviation. And the Gaussian Naive Bayes will store in terms of arrays. 0 means for the first class of A, and 1 means class of B. That's how it's going to store those model parameters. So this is for class A, and this one is for class B. Now, what we can do is we'll use those model parameters like mean and standard deviation, and we can generate new points using NumPy. NumPy has a function multivariate normal distribution. That means he's going to generate new points given the mean and standard deviation. And we are asking to generate 5 new points given the standard deviation and a mean for both the classes. Now let's combine those newly generated points and let's plot the old point and also the newly generated points. And if you notice here, the newly generated points have, yeah, sorry, there was some interruption. So I'm back here. So now with the newly generated point, if you plot those and you notice here that the points pretty much fall within the cluster. So if you see here, the green points are the newly generated points, and they are very much within the cluster of the known data. And similarly, the yellow points also fall within the cluster of the red data. This is great. This is the idea of generating new samples. Let's take a look at where we can use this idea of generation. One use case can be handling class imbalance. So I'm going to use the credit card data, and the credit card data has two classes. One is the normal data, and the other one is the fraud or anomalies data. So that's like 284,000 samples as normal, 492 as the fraud data. What I'm going to do is we'll use the Gaussian Naive Bayes to generate some new samples for this particular class, which is the class of 1 here. So, like in the previous case, we will fit the data, and when you fit, the model is going to estimate the mean and standard deviation for both the classes, and we will generate the new points. Let's say I'm generating 500,000 new points for the class abnormal class, which is a fraud data. And as you know, internally, theta means the mean and the variance means the standard deviation, and for the class of 1, so we can generate new points, not 5 points but 500,000. Sorry about the typo here. And now we can concatenate the new points and the old points, put them in a data frame, refit the Gaussian Naive Bayes, and you notice here the number of errors that is making. Previously, it was making an error of 39 with no generation or no sampling of new data. With the new data having more samples for the minority classes, the error has gone down from 39 to 29. So that's quite significant use case. I hope you can try this as an option of data generation for data generation for other use cases other than class imbalance problem. Yeah, so other than class imbalance problem, this can be also utilized for detecting, let's say, anomalies. You want to detect anomalies, then also Gaussian Naive Bayes can be used because it is estimating the model parameters like mean and standard deviation. You can compare the mean and standard deviation of the samples and be able to say whether these are anomalies or not anomalies. So I hope you found it interesting. We talk about really modern day generative models like transformer and BERT. The naive Bayes can also be one of the options in our data science tools. So that was the demo. I showed the out of core learning, and then after that, we also looked at how Gaussian Naive Bayes helps in data generation. I hope you enjoyed this session, and thank you for your time. We'll see you in some other session. Have a great day.